So if you look at the transformer block over here, you can see that going to the multi-head attention, then you have the outer layer. The next big block is the feed forward, which essentially it's the linear transformation. So also I find this really good visualization for feed forward network.
Of the lesson. What happens inside a multi-layer perceptron?
So that's the feed forward network.
You might think of this sequence of vectors flowing into the block. And remember, each vector was originally associated with one of the tokens from the input text. What's going to happen is that each individual vector from that sequence goes through a short series of operations. We'll unpack them in just a moment. And at the end, we'll get another vector with the same dimension. That other vector is going to get added to the original one that flowed in, and that sum is the result flowing out. This sequence of operations is something you apply to every vector in the sequence, associated with every token in the input, and it all happens in parallel. In particular, the vectors don't talk to each other in this step. They're all kind of doing their own thing. And for you and me, that actually makes it a lot simpler, because it means if we understand what happens to just one of the vectors through this block, we effectively understand what happens to all of them. When I say this block is going to encode the fact that Michael Jordan plays basketball, what I mean is that if a vector flows in that encodes first name Michael and last name Jordan, then this sequence of computations will produce something that includes that direction basketball, which is what we'll add on to the vector in that position. The first step of this process looks like multiplying that vector by a very big matrix. No surprises there, this is deep learning. And this matrix, like all of the other ones we've seen, is filled with model parameters that are learned from data, which you might think of as a bunch of knobs and dials that get tweaked and tuned to determine what the model behavior is. Now, one nice way to think about matrix multiplication is to imagine each row of that matrix as being its own vector and taking a bunch of dot products between those rows and the vector being processed, which I'll label as E for embedding. For example, suppose that very first row happened to equal this first name Michael direction that we're presuming exists. That would mean that the first component in this output, this dot product right here, would be 1 if that vector encodes the first name Michael, and 0 or negative otherwise. Even more fun, take a moment to think about what it would mean if that first row was this first name Michael plus last name Jordan direction. And for simplicity, let me go ahead and write that down as M plus J. Then taking a dot product with this embedding E, things distribute really nicely, so it looks like M dot E plus J dot E. And notice how that means the ultimate value would be 2 if the vector encodes the full name, Michael Jordan, and otherwise it would be 1 or something smaller than 1. And that's just one row in this matrix. You might think of all of the other rows as in parallel asking some other kinds of questions, probing at some other sorts of features of the vector being processed. Very often this step also involves adding another vector to the output, which is full of model parameters learned from data. This other vector is known as the bias. For our example, I want you to imagine that the value of this bias in that very first component is -1, meaning our final output looks like that relevant dot product, but -1. You might very reasonably ask why I would want you to assume that the model has learned this. And in a moment, you'll see why it's very clean and nice if we have a value here which is positive if and only if our vector encodes the full name Michael Jordan, and otherwise it's 0 or negative. The total number of rows in this matrix, which is something like the number of questions being asked, in the case of GPT-3, whose numbers we've been following, is just under 50,000. In fact, it's exactly 4 times the number of dimensions in this embedding space. That's a design choice. You could make it more, you could make it less, but having a clean multiple tends to be friendly for hardware. Since this matrix full of weights maps us into a higher dimensional space, I'm going to give it the shorthand W up. I'll continue labeling the vector we're processing as E, and let's label this bias vector as B up and put that all back down in the diagram. At this point, a problem is that this operation is purely linear, but language is a very non-linear process. If the entry that we're measuring is high for Michael plus Jordan, it would also necessarily be somewhat triggered by Michael plus Phelps, and also Alexis plus Jordan, despite those being unrelated conceptually. What you really want is a simple yes or no for the full name. So the next step is to pass this large intermediate vector through a very simple nonlinear function. A common choice is one that takes all of the negative values and maps them to 0, and leaves all of the positive values unchanged. And continuing with the deep learning tradition of overly fancy names, this very simple function is often called the rectified linear unit, or ReLU for short. Here's what the graph looks like. So taking our imagined example where this first entry of the intermediate vector is 1, if and only if the full name is Michael Jordan, and 0 or negative otherwise, after you pass it through the ReLU, you end up with a very clean value where all of the 0 and negative values just get clipped to 0. So this output would be 1 for the full name Michael Jordan and 0 otherwise. In other words, it very directly mimics the behavior of an AND gate. Often, models will use a slightly modified function that's called the JLU, which has the same basic shape, it's just a bit smoother. But for our purposes, it's a little bit cleaner if we only think about the ReLU. Also, when you hear people refer to the neurons of a transformer, they're talking about these values right here. Whenever you see that common neural network picture with a layer of dots and a bunch of lines connecting to the previous layer, which we had earlier in this series, that's typically meant to convey this combination of a linear step, a matrix multiplication, followed by some simple term-wise nonlinear function like a ReLU. You would say that this neuron is active whenever this value is positive, and that it's inactive if that value is 0. The next step looks very similar to the first one. You multiply by a very large matrix and you add on a certain bias term. In this case, the number of dimensions in the output is back down to the size of that embedding space, so I'm going to go ahead and call this the down projection matrix. And this time, instead of thinking of things row by row, it's actually nicer to think of it column by column. You see, another way that you can hold matrix multiplication in your head is to imagine taking each column of the matrix and multiplying it by the corresponding term in the vector that it's processing, and adding together all of those rescaled columns. The reason it's nicer to think about this way is because here the columns have the same dimension as the embedding space, so we can think of them as directions in that space. For instance, we will imagine that the model has learned to make that first column into this basketball direction that we suppose exists. What that would mean is that when the relevant neuron in that first position is active, we'll be adding this column to the final result. But if that neuron was inactive, if that number was 0, then this would have no effect. And it doesn't just have to be basketball. The model could also bake into this column many other features that it wants to associate with something that has the full name Michael Jordan. And at the same time, all of the other columns in this matrix are telling you what will be added to the final result if the corresponding neuron is active. And if you have a bias in this case, it's something that you're just adding every single time, regardless of the neuron values. You might wonder what's that doing? As with all parameter-filled objects here, it's kind of hard to say exactly. Maybe there's some bookkeeping that the network needs to do, but you can feel free to ignore it for now. Making our notation a little more compact again, I'll call this big matrix W down, and similarly call that bias vector B down, and put that back into our diagram. Like I previewed earlier, what you do with this final result is add it to the vector that flowed into the block at that position, and that gets you this final result. So for example, if the vector flowing in encoded both first name Michael and last name Jordan, then because this sequence of operations will trigger that AND gate, it will add on the basketball direction, so what pops out will encode all of those together. And remember, this is a process happening to every one of those vectors in parallel. In particular, taking the GPT-3 numbers, it means that this block doesn't just have 50,000 neurons in it, it has 50,000 times the number of tokens in the input. So that is the entire operation. 2 matrix products, each with a bias added, and a simple clipping function in between. Any of you who watched the earlier videos of the series will recognize this structure as the most basic kind of neural network that we studied there. In that example, it was trained to recognize handwritten digits. Over here, in the context of a transformer for a large language model, this is one piece in a larger architecture, and any attempt to interpret what exactly it's doing is heavily intertwined with the idea of encoding information into vectors of a high-dimensional embedding space. That is the core lesson, but I do want to step back and reflect on 2 different things. The first of which is a kind of bookkeeping, and the second of which involves a very thought-provoking fact about higher dimensions that I actually didn't know until I dug into transformers. In the last two chapters, you and I started counting up the total number of parameters in GPT-3 and seeing exactly where they live. So let's quickly finish up the game here. I already mentioned how this up projection matrix has just under 50,000 rows, and that each row matches the size of the embedding space, which for GPT-3 is 12,288. Multiplying those together, it gives us 604 million parameters just for that matrix. And the down projection has the same number of parameters, just with a transposed shape. So together, they give about 1.2 billion parameters. The bias vector also accounts for a couple more parameters, but it's a trivial proportion of the total, so I'm not even going to show it. In GPT-3, this sequence of embedding vectors flows through not one, but 96 distinct MLPs, so the total number of parameters devoted to all of these blocks adds up to about 116 billion. This is around 2/3 of the total parameters in the network, and when you add it to everything that we had before for the attention blocks,
So essentially we have 96 these repetitive layers. Each layer you have this attention plus this feed-forward network. And this one gives you a very nice summary of now every time we talk about how large the model is, this gives you a very nice distribution of where does this model, this weight coming from. So you can see that actually here, the feed forward, this up projection, down projection, that's the feed forward part, right? That's actually gives you the most of the parameters.
The embedding and the unembedding, you do indeed get that grand total of 175 billion as advertised.
So that's where the that 175 be coming from. Okay. So one thing I do want you to notice is that if you look at the distribution, then you may notice that the weight from the feed-forward network is much larger than the K2 and the V matrices, right? So the implication of that is when you are doing the calculation, the attention layers are going to mostly dominate by the computation. So, because the memory, because if I'm sure you took some computer architecture class, you have the processor, you're grabbing the data and do the computation, right? So, some of them are computation bound, some of them are memory bound. So in here, when the processor are processing the attention map, it's computation bound. Because you can see that we don't need a lot of weight, but we need a lot of computation. Okay, but whereas the feed forward network, the layers usually are memory bound because means that the memory is dominating the latency. Make sense? Because
it's probably
later when we are talking about how to speed up the computation of the large language model, we will get back to this. But now I just want you to give this idea, and that's just 96 times of this repetitive process, and also here give you 1.2 billion for each block, or each layer is 1.2 billion parameter times 96 and 600 mega times 96.
Mentioning there's another set of parameters associated with those normalization steps that this explanation has skipped over, but like the bias vector, they account for a very trivial proportion of the total. As to that second point of reflection, you might be wondering if this central toy example we've been spending so much time.
Uh, now it's good. Right. So this one, just give you this very again, this slides give you just a very high level of the feed-forward network, but the video explained this up and down very well. Okay. Alrighty. So and also like you can see that this add and the normal. So the layer normalization, it's very similar to the batch normalization we learned before. Essentially, we are normalize all the values in the layer, and also like we are going to have two learnable parameter the gamma and the beta to transform it back if it's really important. So by putting everything together, we have two different designs. This is post norm and the pre-norm. The pre-norm essentially is what I showed you earlier. You have this linear layer. I'm sorry. The pre-norm. Wait. I think it's the slides was not the I'm sorry the post norm it's what's more popular nowadays because you can see that like it's the multi-head add a norm feed forward and add a norm, so that's the architecture. So the part of that we haven't so far is that we haven't touched is this positional encoding. So when I at the very beginning I was asking you if you were designing this the simplest way is just assign a number to each position, right? But apparently that's not the best way. Why? Um, so So why the simply assign a number to the position and append that to its or add that to the original embedding is not a great idea. There are many reasons, but one of the reasons is that if you think about it, all the embeddings the numbers are really small numbers, right? So each number in the representation vector usually are very small real numbers. When you are adding a big natural number to that vector, that will dilute original embedding information. So in order to fix that problem, people propose this method, how to assign a unique encoding for each word in a sentence. So the function, this is a quite interesting idea. So if you look at this. So this is organized, the tokens here are organized in this dimension here. So you can see from 0 all the way to 50 in this particular example. It means that like in this whole context, we have a total 50 tokens. And now we want to assign a unique vector to represent like which position it is. Okay. And here, of course, we can also use actually one hot encoding because that also gives you this unique representation. But what this method does is that for each token, I'm going to also have a I-dimension vector to represent where this token is, the position. And how is this vector basically, how is each this whole row constructed here? It's like this. So this equation, it's a little bit hard to understand. So let me try to break this down. So it's constructing the each value in this vector in a very particular way. So let's first look at this. So you have this sine function, and this sine function, which is a function of t and the wk. And the t basically is this token index, which is 1 all the way to 50. Okay? And the wk is this equation defined by this equation here. But what is k? K is something related to the dimension index. K is related to the dimension index. So if the k is 0, okay, so you have wk w0, which is w0 and give you this one number, which gives you this one number. And then therefore, for a particular cell over here, let's say token 0 and dimension 0, you are going to be assigned a value which is defined by the sine function. Does that make sense? So basically, this particular cell over here, this 0, 0 cell, is a function of this t and the k. And for this one, for this cell, t is 0. For this cell, t is 0 because the index is 0. And the k is 0. And the k is also 0. And then that will give you this wk, and therefore t and the k uniquely determines the value of this cell. Does that make sense? Okay. Now, if we look at this first column here, what happens is that for this whole column, the wk is all the same. The wk is always the same for the first column. But the t keep changes. Does that make sense? And therefore, you can generate a sequence of whole column value. But what is the meaning here? If you are familiar with the signal processing, this sine will give you a sine function. And the W essentially is determine the angular value, which basically kind of determine what's the frequency of this sine function. And the frequency, as well as the t, the time, actually uniquely determines a value in the sine function. Let me see if I can. The student with the mark didn't come. So if you can visualize, let's say like a sine function essentially is a repetitive function, right? It's a wave. Does that make sense? And basically, the wk value determines the frequency of the sine wave. And the t is the x-axis. So basically, each unique wk and the t determines a point, a value in that sine wave. Okay? And therefore, on this whole column, you can think of basically we are getting a bunch of values in that sine wave according to the time t. Does that make sense? Does that make sense? Okay. And then the second column is determined because I is a odd number. Okay. So the second column is determined by the cosine function. Does that make sense? And the frequency is still the same, which is WK. Then the T, the second column here, basically is determined by the cosine function. Okay? And then look at the third row. So 0, 1, 2. The third row basically is 2. I'm sorry, the third column, 0, 1, 2. Does that make sense? Okay? And then it's going to, therefore, K now becomes 1. The K over there becomes 1. So now it's sine WK and the T. And what does that mean? So when the K becomes jump from 0 to 1, if you look at the WK equation, if you are changing the K from 0 to 1, the W will become what? So when the K increases from 0 to 1, right? So WK will decrease, right? So that means that the frequency becomes slower. Does that make sense? So now you got a different sine wave, but with a different frequency, with a slower frequency sine wave. And then again, based on using the T as the index, basically you are sampling the value from another sine wave with a slower, smaller frequency. Does that make sense? And then like sine, cosine, sine, cosine, and repeat this all the way to the last dimension. So this is a very interesting idea. What that means basically says, well, when I'm constructing the positioning index, the first element, like across all these changes rapidly because the frequency is high. So when you are changing the T, the value actually kind of changes frequently. What that means is that if you have a lot of if the token the context is very big, what does that mean? So remember, what happens is that we have a sine wave, and the T basically is the time, and you are starting to keep sampling the value in the sine wave, and use that value as the value in the first column. Okay, so when the context increases, what does that mean? You are going to repeat, right? You're going to repeat, and actually you're going to repeat fast because the frequency is high. So like once you're up to a certain T, then you have to sample in the same position. Does that make sense? So that's bad because the whole point of positioning and coding is that we want them to be different, right? But the smartness about this is that this is going to give you, even though the first column is going to repeat, the last column is going to be a very slow sine wave, right? So therefore, the last column is going to be very hard to repeat. So you can think about a different way to think about the design is that, let's say like the first column, let's say like we only have 3 columns here. The first column, we are using the seconds to number them. So 1 all the way to 60. The second column, we are using minutes to number them. The third column, we are using hours to number them. So by combining the minutes and the seconds, minutes, and the hours, you can have you can have all these different encoding for the position. Does that make sense? So this one gives you, and then you may wonder like, why are we going through all these troubles to do this positioning and coding, right? So the basic idea is that when you are doing this, when you are adding this positioning encoder, this vector to your original to the word embedding, and by doing the inner product, this equation can help you to quickly calculate absolute distance between two tokens. Okay, so that's the figure here is exactly showing that. So this one basically showing that like if from the 0 to 50, and you can see the gradient change, and that can easily calculate the relative distance between any two tokens in this whole context. Okay, and later you are going to see an even more tricky encoding that's used in the modern the Facebook Llama models. But that's how we are designing the positioning encoding. Okay, so now we are, if you look at the figure over here, now we pretty much have everything, right? So let me put everything back together, just, what we have learned so far in this lecture. The tokenizer giving all the inputs in this whole context, your prompt, basically. Your prompt going to be, going through this array for both input and output. So the output is the ones that you saw, it was generated by you before. The input is the new token you are seeing, right? So both of them going through position and encoding, okay? And both of them going up the tower, going through this multiple head attention. And that's all the things that we learned. And add and the norm. Did I explain the add? I think the video explained the add, but let me mention this one more time. So if you look at the add and the norm, essentially is that original embedding comes up here. And by giving all this attention, you are adding the shift, right? The video explained that. So the original embedding, adding the delta E together, basically you are shifting the original representation to a different angle, right? And then you go up to the feed forward, you do another add and norm. And then like for the output, the decoder here, the output embedding going through this masked multi-head attention. Why masked? Because this basically masked is the half attention table, means that like I'm not cheating by looking at the future, because this so far what I have already generated, right? I want to use what I have already generated and what I should do next. So it's a masked multi-head attention going to add a norm, and then these two vectors. Now we are doing a cross attention. What does that mean? So the cross attention, the bridge here is doing the cross attention. So in the self attention, we see that on the column itself, on the row is also itself. You are trying to measure, like, how this word is related to its context, right? But the cross attention, the column is from, for example, from one side, the row is from another side, and you are calculating attention map. What that is that, well, so when you are doing the cross attention, the Q comes from the right-hand side. The key, I'm sorry, right. So the Q comes from the right-hand side, and the key comes from the left-hand side. What that means is that, well, based on what I have generated so far, what are the information I need to know from all the prompts, and what I should generate next. So I'm trying to grab so the decoder is trying to grab the context information by doing the cross attention with all inputs. Does that make sense? So by doing this, now essentially I learn all the context information from my surrounding words, but also from the inputs. Okay, and then like finally going to another feed-forward network and another linear and softmax for giving you the final output. So this is called encoder-decoder architecture. So results. So when attention paper was first published, people started trying to compare transformer with all the previous the recurrent neural network, the one-way CNN, and all that, like attention beats them all with a fraction of the training cost. So that's why now it's attention is all you need. Okay. Now, based on this, figure, we are going to talk about some design variations. The most so most of the design variations, some of them are optimization, some of them are just different design choices. So first, I'm going to talk about this different encoder decoder, encoder only, and decoder only. GPT, what we have learned so far in the video, it's GPT, it's a decoder only. So let me talk about all these different architectures one by one. So the encoder decoder architecture is quite popular in doing this traditional natural language processing tasks. It offers a unified text-to-text model for transfer learning on various NLP tasks. Translation, acceptability, semantic similarity, summarization, and let's see what they are. So this is actually the T5. What T5 stands for? Do we have the name here? T5 text to text transformer something. So there are 5 T's in this name. So it's called T5. Do we have a name somewhere? So it's text to text, a transformer something. And that's the architecture over here. So it's pretty much the figure. This is basically expanding the figure that we have been showing you all the way here. So for example, like let's say like if this is a translation, let's translate English to German. Okay. What we have is that like the whole English words are the input. Okay. The whole sentence of English is the input. And you are going to do all these, encoding blocks, and you got all those vectors over here. And then, like for the decoder block, is that the part that you want to start to generate the German words, right? So what happens is that, well, first, the first Y0 over there, the Y0 over here is going to attend with all these, vectors over here. And then you are using the decoder block to generate one word. Okay. And then in the second iteration, this output plus the BOS, this is 2 words now, is fed into the decoder. Okay. And then also it's going to attend with all the original input. And then generate the third word. And then in the third word, then the first 3 tokens are going to be attended with all the inputs and generate the 4th word. Okay. And doing this autoregressive way until you translate the whole sentences. So basically the idea is that if you think about the idea basically is that, well, if you look at the whole sentences of English, well, now what's the first word? Okay. And once I generated the first word, basically what the model says, oh, this is my first word. And based on my first word and your original English plain text, what should be the next German word, right? So this is, therefore, for this kind of text translation, this encoding decoding block works very well. Okay. And if you think about it, then in this encoding block, all the attention should be global attention, right? Because you already see the whole sentences of this, all the original English text. But inside of the decoder block, all the attention should be, the self-attention should be masked self-attention, because I can only see the words I see so far. Does that make sense? Okay. And then inside the cross attention, all these arrows here, the cross angle here, those are the cross attention. Basically, the query from the decoder is going to ask the keys from the encoder. Says, oh, this is my German word. Which English words should I pay attention to translate next word? Does that make sense? Okay, so that's how the T5 works. This encoder-decoder architecture. Okay, so the second design is the encoder only. We only need the the left half, the left tower. We only need the left tower. We don't need the right tower. And the BERT, usually it's for the tasks like training like a mask language model. For example, what happens is that, well, the input is the movie is very something exclamation and asks you to predicting what is that missing word. Okay, so for this kind of task, I can see the whole sentence. I can see the text before me. I can see the text after me. I just need to predict what's the missing word over here, right? So therefore, in this way, I only need the left tower, which is doing the global attention. Does that make sense? So this is the idea of BERT. Okay. But for GPT, it's totally different. For GPT, basically, by looking at the prompt, I need to constantly just keep generating what's next word, right? So the GPT is a decoder only transformer, because if you think about it, if I just need to keep generating what's next, then like I can only look at what has been generated so far, right? So that's why like we only need to use this decoder part of it to do this. So if we go back to this figure here, so all the things that we have learned about GPT, we only needed the right-hand side. And for tasks like the filling the missing piece, we only need the left-hand side. And for translation, text translation, we can have both left and right side. So this just basically for different tasks, you need kind of like different components. Okay. And if you think about it, the main difference between the encoder decoder, basically it's the way that you are doing the attention is different. The encoder is always doing global attention, and decoder is only always doing masked attention. Does that make sense? So the next thing we want to talk about to change the absolute positioning encoding to relative positioning encoding. Why? So the basic idea is that the absolute positioning encoding, it's going to run out one day. And then like we are going to repeat, right? But really, when we are thinking about the positioning, we don't really need the exact absolute positioning location information. What do we care about when we are doing the language processing? The only thing we care actually is about the relative position of these two tokens. Does that make sense? So therefore, the idea of relative positioning encoding. They have different ways to do relative positioning encoding. So one way is to provide the relative distance information by impacting the attention scores. And let me show you what that means. So this work called alibi, attention with linear biases. What it does is that instead of adding the positioning encoding into the original embedding, it's adding this relative information and added that into this attention map. So therefore, the relative positioning encoding, the relative position, and you can see that like 0, -1, -2, those are the relative position of these two tokens. right? And adding to the K to the attention map. And the idea is that, well, by doing this, location, this position information is only impacting K and the V, but not the, I'm sorry, the Q and the K, right? Not affecting the original meaning of the V. Basically, that's the idea. This another idea is this rotary positional encoding, this rope. So this is the current, most of the SOTA large language model is actually using this. And let's see, let me explain. Again, all the math looks really scary, but let me try to break this down and explain what's going on here. So what it does is that for a embedding over here, for this embedding over here, it's going to break this embedding into a lot of different pairs. You can see the color here, the two blue, well, two green, two red, two pink, two yellow, and two blue. So this whole embedding is chopped into many small pieces. Each piece has two elements, okay? And we know that for a vector of two elements, essentially it determines one location, right? And then it's using this so-called theta to rotate. And this, this location determines one vector, right? Right. So it's rotating that vector by a theta angle. Does that make sense? So you are rotating this vector by theta angle to get a new vector. And that's how you are doing for this whole vector. And then what happens is that you can see that it has a theta 1, theta 2, all the way to theta d divided by 2. It means that, what it means is that I'm going to rotate a different degree for each small vector over here. So inside this original embedding, I'm chop them into small pieces to a group of two elements. So two elements determines one vector, right? So for each vector, I'm rotating a different angle to get a new, and use that rotation as the embedding for the positioning. Okay? Okay. So what are the equation here, like x times e power to mi e here? What that means is it's a calculation in complex number. And what that number essentially is equivalent to, when you are doing this, is essentially it's equal to you rotating the x by these degrees. Okay, so that's the equation in the complex math. And then like the idea is that why this even work? Why we are even doing this? So the idea is this. While when we are doing a inner product of these two vectors, so this is one vector after the encoding. Okay, see, so the encoding basically says original encoding x, right? And by doing this m, I'm going to get a new encode embedding with the positioning information, right? So when I'm doing an inner product of this embedding and this embedding, okay, and by doing the complex number math, essentially finally you are going to get this, which essentially the inner product of these two embedding equals to query times k, the query times k, which is the attention, right? and rotate by m by minus n degrees. And this m minus n is going to give you the relative position of these two tokens. Okay? So that's how you are this llama doing its own positioning and coding. But in reality, when you want to do this, apparently we can't, in the matrix, we can't do the complex number, but how do you rotate a vector? So we do that by multiply with this matrix, and it's equivalent to doing the rotation. And this is the rotation matrix. And if you look at the rotation matrix here, essentially, when you are multiplying a vector, the original embedding, with this rotation matrix, you can see that essentially it's keep rotating the first two elements, the second two elements, the last two elements. It's equivalent to as you are dividing the embedding into multiple pieces and each piece rotating by a certain degree. Does that make sense? Okay. And why like llama want to do this? Why we are not, why it's better than the absolute positioning and coding, right? So the idea is this. When the model like llama, if it's originally trained at the context of 2048, okay, but now suddenly you are giving an extra token to the model, which is 2049, right? Once you do that, the position encoding still works. It just give you the new position encoding, right? But that is a position encoding. The model was never trained. Does that make sense? The model was never trained. Therefore, when you are giving an extra token to the context, then the model will suddenly becomes do not know how to handle that extra positioning encoding. So basically what that means is that if you train this model with the context of 248 tokens, means that the prompt can only have 2048 tokens. And when you are using it, when the user is using it, and give you a super long context, which exceeds 2048, the model's capability will suddenly drop because it does not know how to handle that. Does that make sense? Does that make sense? But by doing the relative position encoding, it uses one trick. Is that it's instead of giving the extra positioning encoding beyond the 2048, it's actually trying to compress. It's trying to compress the context window and assign. If you compare these two figures here, you may notice that there's a middle point over here. What that means is that if you give me, let's say, like originally the token was trained in 2048, now you give me a prompt that exceeds 2048, I'm going to give a new positioning encoding in between these two original encoding. Okay, and by doing this, suddenly I can handle, I can interpolate the positioning encoding for the new tokens. Let's say originally, let me use a small example so you can actually try to understand this. So let's say originally I have the context is 4 token, means that the prompt can only accept the 4 tokens, like I have a cat, okay? And each word has 1, 2, 3, 4 for position encoding, right? Now, suddenly in the original absolute encoding, if you give a prompt with 5 words, then the 5th word will have a position encoding of 5. Then the model will crash because I never see that. I was never trained it. Okay, but with the rotational encoding, what you can do, give you the capability is that if you give me like a 5 or even 8, let's say you give me a prompt with 8 words. Now I'm going to give 1, 1.5, 2, 2.5, 3, 3.5, and using this interpolate this positioning encoding for these actual words. Does that make sense? But why? But then you may ask, well, 1.5, 2.5, and 3.5 was never trained for this model either. The model was never trained with the position 5, but was never trained with the position 1.5 either. Right? Right. So now the interesting observation is that because the way we are training, because the neural network is, the model is much better at interpolating than extrapolating. When you are training the model with the position encoding of 1 to 4, it's very hard for the model to predicting what's beyond the scope. But it's very easy for the model to understand within the scope. Does that make sense? So the rotation encoding can give you a much better capability in handling context much bigger than the original was trained. Yes.
So you don't need to retrain the model.
Good question. So if you think about it, when you are assigning 1, 1.5, 2, 2.5 to the new token, like 8-word prompt, what happened is that now something is off because originally 1, 2, 3, 4 are assigned to those 4 words. Now 1, 2, 3, 4 are assigned actually to a different set of words, right? So therefore, actually, yes, once you are doing the reassignment, you need to tune a little bit, but you only need a very small amount of data to tune this for the model to accept a prompt much bigger than originally was planned. Does that make sense? That's why in Llama now it's using this rotational position encoding. Okay. So let me try to finish at least this part, and we are going to talk about more about large language model next week. So next is KV cache optimization. It's relatively easy to understand. So the way that we have learned so far doing the attention, so far what we have learned attention is that, well, for when we have a very long context, the last token needs to append with all the previous tokens, right? What that means is that if I have, like, we already showed you that huge table, right? So if you have a if you have a very long context window, which is what we want to have, because because the longer the context window is, the longer it can remember your history, right? But that means that you need to remember the KV cache for all the previous tokens. Does that make sense? And what's even worse is that, remember, we have multiple heads. Each head, you need to remember all the KVs, Ks and Vs. That's huge. And that's a lot of computation. Okay? And the KV, the memory is huge. Okay. So people did a lot of optimization. Actually, remember when first time DeepSeek came out, we made a news because it's so fast, same accuracy, but much less training cost. One of the optimization is this KV cache optimization. What it does is basically, well, this one gives you, all the math. Basically says, well, if I have a context of 4096, you need 160 gigabytes to store all the KVs, which is not realistic. Okay, so one of the things the DeepSeek optimize basically is this multi-head attention. What it does is that, well, instead of, because you have multiple heads, so instead of remembering the K and the V for all the heads, I'm going to only remember the K and the V only for that one head. And the other, let's say if I have 15 heads, okay, I only remember K and the V for one head. And all the other 14 heads do not have KV at all. But then what it does, it's going to attend with only that single head's KV cache. Essentially, you are eliminating the need of all those heads KV cache. Does that make sense? And then like people find out, oh, that if you are, remember the reason that we are having multiple heads is that we are trying to ask the multiple heads to capture multiple different kind of aspects of the relationship, right? Color, shape, size, and all that, right? If you just have one set of KV and use the same set of KV for all the heads, kind of lose the purpose of using multiple heads, right? It still can like, encode the information with that single set of KV, but not as good as the 15, okay? Then like people say, oh, we can just do a trade-off. Okay, instead of like keep one set of KV, let's say like, let's keep 2 sets or 4 sets, okay? If I have 2 sets, then half of the heads are sharing one set of KV and half of the heads sharing one set of KV. Does that make sense? Or if I have 4, and so different model, they have different sets. So basically, I'm using a group of heads share a same set of KV. Another group of heads sharing a same set of K and V. Does that make sense? So by doing this, you are reducing the KV size. And of course, there are still have some other optimizations to trying to reduce the KV cache, but this is one of them. So multi-head, multi-query, and a grouped query. So that's kind of the idea. So this one gives you the results. So people show that, the blue line is the KV size for multi-head, and the red line is for the multi-attention. So like multi-query. So all the query use the same set, and the green line is the one that use like several groups share one KV set. Okay, so people find that like while the multi-query sacrifices the accuracy, but the multi-group sharing one KV actually maintains the accuracy by reducing the KV cache by 8 times. So you can see that this is the accuracy comparison. Look at the last column, you can see that the group query maintains the same accuracy of the multi-head attention. Okay, so that's, I'm not able to finish all of them. So that's all. So let me explain the last optimization is for the feed-forward network. So this is a gated linear unit trying to optimize the feed-forward network. And I'm also going to explain these next week. And then like we are going to talk about the actual large language models, some the ideas. And also the optimizations, how to do the pruning, quantization, and all that for large language models. Okay, all right. So that's all for today's class then. Thank you.